Hi, in this lecture we are going to talk about insertion sort. So, let's get started. It is a simple sorting algorithm that builds the final sorted array one item at a given time. It has quadratic running time, so ordo n squared, as we have discussed for bubble sort or selection sort. On large datasets, it is very inefficient, but on arrays with 10 to 20 items, it is quite good. This is what we have been discussing for selection sort as well, that on huge datasets, of course, it's not going to work fine. This is why better algorithms came to be, such as merge sort or quick sort. But on small arrays with 10 to 20 items, it's working quite fine. And it is very simple to implement. So as we have seen for selection sort, it is also true for insertion sort that it has a simple implementation. It is more efficient than other quadratic running time sorting procedures such as bubble sort or selection sort. And it is an adaptive algorithm, so speeds up when array is already substantially sorted. It is stable, so it preserves the order of the items with equal keys. It is an in-place algorithm, so doesn't need any additional memory for the sorting operation. And it's very important that it is an online algorithm. It can sort an array as it receives it, for example, downloading data from the web. Hybrid algorithms uses insertion sort if the subarray is small enough. For example, merge sort and quick sort switch to insertion sort when there are only 10 to 20 items in the subarray. So insertion sort is faster for small subarrays than quick sort, for example. And a variant of insertion sort is the so-called shell sort. We are going to talk about shell sort in the coming lectures. Okay, so a good question is that what to use. Selection sort and insertion sort are quite good algorithms for small arrays. They are very similar algorithms, but insertion sort requires more writes because the inner loop can require shifting large sections of the sorted portion of the array. So in general, insertion sort will write to the array ordo n squared times, while selection sort will write only ordo n times. So as you can see, selection sort is going to be better in this aspect. So for this reason, selection sort may be preferable in cases where writing to memory is significantly more expensive than reading, for example, flash memory. But anyways, if the writing operation is not that expensive, then we usually favor insertion sort. We are going to implement merge sort and quick sort to use insertion sort as a sub-procedure. Okay, so let's take a look at the source code. We have an insertion sort method with a one-dimensional array of integers, for example. We iterate through the arrays. We initialize the j index to be equal to the I, and while the j index is greater than 0 and the array j minus 1 is greater than the array j, what does it mean? That the item before the j index is greater than that given value with j index, then we swap the two. So we keep swapping the array with the j index and the j minus 1, and we keep decrementing the value of j. And it is a while loop, so we keep doing that while the items before the j index, as you can see, while the j is greater than 0. So what's very important, that there's going to be lots of shifts, as you can see. Of course, if the array are substantially sorted in the sense that there are several items in its sorted positions, then this algorithm is going to be a bit better. This is why we have been discussing that it is a so-called adaptive algorithm. Okay, so we iterate through the array sequentially. Then while the previous item is greater than the given one, we keep swapping them. That's why there are so many shifts in the insertion sort. So let's see a concrete example. We have a one-dimensional array of integers 55, minus 2, 34, 10, 0, 2, minus 5 and 12. Okay, of course we start at the beginning. It is the first item, so that's all. Then we consider the next one, and basically we keep considering whether the items before that given actual one is smaller or greater than that given one. 55 is greater than -2, so we shift it. And basically that's the only item we have to consider, so that's all. Okay, what about the next one? It is 34. We have to consider every single item that precedes that given 34 number. 55 and -2. 55 is greater than 34. Yeah, so we shift it. -2 is greater than 34. No, so it's going to be just fine. Okay, what about the next item? The 10. Again, we have to consider every single item that precede the number 10. 55 is greater? Yeah, we shift it. 34 is greater than 10? Yeah, we shift it. -2 is greater? No, so it's going to be just fine. Okay, what about 0? 55 is greater than 0. Yeah, we shift it. As you can see, there's going to be lots of shifts. This 55 has been shifted from the beginning. Okay, 34 is greater than 0. Yeah, we shift it. 10 is greater than 0. Yeah, we shift it. And -2 is greater than 0. No, it's going to be just fine. What about 2? 55 is greater, of course we shift it. 34 is greater than 2, yeah, we shift it. 10 is greater than 2, yeah, we shift it to the right. 0 is greater than 2, no, so this is where we have to insert the number 2. What about -5? Oh, there's going to be lots of shifts, because 55 is greater than -5, 34 is greater than -5, 10 is greater than -5, 2 is greater than -5, 0 is greater than -5, and -2 is greater than -5, so we have to make lots of shifts. What about the last item, the 12? 55 is greater than 12, yeah, we have to shift it. 34 is greater than 12, yeah, we shift it. 10? No, it's smaller, so this is the place for the number 12. So this is how we sort an array with the help of insertion sort. As you can see, there's going to be lots of shift operations, and that's why if we have flash memory, for example, then selection sort is going to be favorable. So that's all about insertion sort. Thanks for watching.